Okay, we're going to talk about maybe the most important thing that I will teach you in this entire summer course. And it has to do all with similar triangles and the ratio of the sides of similar triangles. So we're going to take a look. I've got two 30, 60, 90 triangles here. These are all right angles. I just don't have them marked. And there we go. I'm going to go ahead and mark them for us so we don't forget. And what I'm asking is to find the ratio of the side opposite the given angle to the hypotenuse. Now, every right triangle has a hypotenuse. And in the past, we've kind of been talking about short leg, long leg, hypotenuse as a way to talk about the different sides. But of course, on a 45, 45, 90, we don't have a short leg and a long leg. The two legs are the same length. And we might look at a triangle in the future where we can't really tell which side is the long leg and which side is the short leg. So instead of using that language, we're going to switch and become a little more rigorous. We're going to talk about the sides of right triangles in terms of the angles that are in those triangles. So I'm looking at the opposite side, the side opposite the angle. We've already talked about the opposite side, right? The opposite side is just this side over here. And then the opposite side of 45 is this side over here. The opposite side of 60 is this side over here. And so now we're going to talk about, there's an angle, that's a theta right there. That's just a variable that we typically use when we talk about angles in mathematics. So the side that's opposite theta is this opposite side. The side that's adjacent theta is this adjacent side, right? Now, of course, there's two sides that are really adjacent to theta, the adjacent side and the hypotenuse. But the hypotenuse is across from the 90-degree angle. We're always going to call the hypotenuse. Now, knowing where the opposite and adjacent and hypotenuse are really depends on where the angle is. So if I moved my theta up here, then, well, now this side would actually be opposite the theta, and this side would be adjacent to theta, and then I'd have my hypotenuse would still be in the same place across from the right angle. Okay. So we want to find the ratio of the side opposite the angle to the hypotenuse. So we're looking for the ratio of this side to this side, and I'm asking for it in simple stratical form. Well, how do I get that in simple stratical form? Because right now, if I measured it, and I went up here and I said, let's measure that ratio, opposite over hypotenuse, BC over BD, I get 0.5. Okay, well that's interesting. I can come down here. That looks like it looks exact, right? 0.50. Maybe that's really just 1/2. We'll see. I can measure the ratio down here on my 45, 45, 90, okay. And I can measure the ratio down here on my 30, 60, 90 again. Okay, and this is what I get. I get a 0.5, a 0.71, a 0.87. And I bet if I extended so that I had a little bit more, there we go. I bet if I extended so that I had a little bit more decimal points here, we'd see this kind of going off and continuing to be decimal. Sketchpad is just rounding all of these to the hundredths place. So what about if we wanted the ratios in the simple stratical form? What we would need is to remember that we know the ratio of the sides, right? We've already talked about, and if you haven't done this yet, that means you need to go back and do the beginning of lesson 12. So I have x root 3, and I have 2x. So if I was going to do the opposite side over the hypotenuse, then really what I'm looking at is that opposite over hypotenuse is equal to x, that's opposite 30, over 2x. And so we're looking at opposite over hypotenuse when we're looking at a 30-degree angle. Is x over 2x? Well, the x's are going to cancel out, and I just get 1/2, which is 0.5. All right, great. So what if I do that down here? So I'm going to do opposite over hypotenuse of a 45-degree angle. And what's this going to equal? Well, opposite the 45-degree angle is an x, and the hypotenuse is x square root of 2. The x's are going to cancel out, and so then I'm going to get 1 over the square root of 2 But then we have to rationalize the denominator, right? So we're going to multiply by the square root of 2 over the square root of 2, and this is going to equal the square root of 2 divided by 2. So, right, because I'm multiplying by root 2 over root 2, and root 2 times root 2 is 2. Okay? Now, it might be a little harder for you to know what root 2 over 2 approximately would be. But we can see when we type it in that I can do the square root of 2 and divide that by 2, and ta-da, I get 0.707107, and that will continue going on. This is an irrational number, and so just saying 0.71 is not sufficient. Over square root over 2 is our simplest radical form. Okay, and then finally, I'm going to do the opposite of our hypotenuse of a 60-degree angle. So I look at the 60-degree angle, and I look at the opposite. Opposite is x root 3. The hypotenuse is 2x. The x's are going to cancel out. I get the square root of 3 over 2. And when I calculate the square root of 3 over 2, I get 0.866025. That's going to keep going, and that's where that's rounding to 0.87. Okay, so what do we notice? Well, as the angle gets bigger, what's happening to the ratio? Well, it's also getting bigger. I wonder if that's always going to happen, right? So we can think about some other angles in between the angles that we have right here, the 30 and the 45 and 60, and say, well, wait a second. What would I expect? I had a right triangle, but instead of having a 45-degree angle or a 30-degree angle, it was a 37-degree angle, right? So close to right in between. What would I expect from a 37-degree angle? What would the ratio be of the opposite side of our hypotenuse? Well, if you're kind of following this pattern, right, it might make sense to you that opposite of our hypotenuse of a 37-degree angle would be somewhere in between the opposite of our hypotenuse of a 30 and the opposite of our hypotenuse of a 45. So maybe we would guess, put question marks there because we're really just guessing, right smack up in the middle, right? Maybe it's 0.6. The opposite of our hypotenuse if we use a 37-degree angle. Now, 0.6 is probably not exact, but, you know, that makes sense. There's 0.5, there's 0.71, maybe it's 0.6. Well, let's check and see. Okay, so let's look at a couple triangles with 37-degree angle in them. So here's two right triangles. These two right triangles both have a 37-degree angle. So let's see, what's the ratio of their opposite side over their hypotenuse? Oh, look at that, 0.6. Interesting. Oh, these silly letters, J and K, all right. So I get 0.6. Well, what about if I did this one? Well, before I even go ahead and measure this ratio, you all should be telling me, well, that's a stupid thing to even have to do, right? Because what do I know about these two triangles? Well, I know these two triangles are similar, right? And so if this one has this side over this side being 0.6, then that's going to be the same thing with this side. And in fact, it is. Okay, in fact, it is. And this is another situation where it does kind of look like we have an exact number, right, at that 0.6, but this is just Sketchpad. Let's see, if I do this divided by that, you see how that is still going to keep going, right? It's not just 0.60, it's just cutting off the 1/8 because it's rounding. But this is an irrational number, but it's always going to be the same. If I have any right triangle with a 37-degree angle, the opposite side of the hypotenuse is always going to be about 0.6. All right. So let's just say we remember this. Let's write it over here. Opposite over hypotenuse of a 37-degree angle is about, I wonder if they have a about sign. There we go. It's about 0.6018 if you remember. All right. So let's remember this. And let's put these triangles away. Oh, get all the stuff out of our way. We're going to look at this new triangle. Here's a triangle where one side is 5. We have an angle of 37. We want to find x. Well, wait a second. How do we do that? We don't have another triangle that's similar to this triangle. Well, all we need to do is remember this ratio that we have. Opposite of our hypotenuse of 37 is equal to 0.6018. Well, let's see. The opposite of our hypotenuse in this case is 5. 5 is opposite of 37. X is the hypotenuse. And so opposite of our hypotenuse should equal 0.6018. So how do I find x? Well, I multiply both sides. So I get 5 is equal to 0.6018 times x, and then I divide. So 5 divided by 0.6018 is going to give me an approximate value for x. And so as I calculate that, and I get 5 divided by 0.6018, I get 8.31, and so this is my approximate value for x. So notice all I needed was one angle in a right triangle and one side length, and I could find another side length by remembering that opposite of hypotenuse of a 37-degree angle is always 0.6018. All right, so that's kind of interesting. And let me see if this is really, yeah, that's really 5 centimeters, so let's see how good we were on this. Measure length 8.31. Okay, so now we can use this sort of tool of remembering the ratios to find different side lengths of right triangles. Okay, so we can continue doing this for all sorts of angles, right? Here's a 32-degree angle, and the opposite of hypotenuse with a right triangle with a 32-degree angle in it is going to be 0.53, and I can see that as I construct this triangle, and I measure this side, and I measure this side, and I take the ratio, I get 0.53. And then I did that again for a 33-degree angle. We already did 30, 35, 41, 44, 45. We know we already had 37, right? Was 0.60. And you can see there's a nice little pattern here. And so if we could just remember what each one of these were, then just like before, if I had the angle and I just knew one side length, I could find the other side length. So now I just need you to start memorizing each one of these opposite over hypotenuse ratios. And then we'll do adjacent over hypotenuse, and we'll do opposite over adjacent, just so that we have all these ratios memorized. Okay, I hope you don't think I was being serious, because to memorize every single one of these ratios would be absolutely impossible, especially because we're not even thinking about like the half angles. What about a 31.5 or a 30.1? All of those ratios are going to start changing. So it'd be really great if there was a way that would remember all these ratios for us. What I want you to do is grab your calculator and pull it out. You need to change it to degree mode. So go to mode, and where it says radian and degree, you're going to switch that over to degree. And then look for the button on your calculator that says SIN. That really stands for sine. And if you put in the sine of 37, then you will get 0.6. If you put in the sine of 41, you will get 0.66, yada, 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 because this is all just cutting it off. So the sine button on your calculator, if an angle is a right triangle, or angle theta is in a right triangle, then the sine of theta is the ratio of the opposite side of theta to the hypotenuse. So here you see my diagram, and then also you can see here that I can go through and calculate the sine of each one of these angles, and I get exactly the same ratio as I did there.